Hi everyone. Today's lecture will be in continuation with the last lecture. So let's begin. I missed vector triple product in the previous lecture. So geometrically, vector triple product of three vectors, say A, B and C, which is usually written as A cross B cross C or A cross B cross C. So A cross B cross C is a vector lying in the plane containing the vector B and C or plane containing vector A and B. So since A cross B cross C is a vector lying in the plane containing the vector B and C, so it can also be expressed as a linear combination of these vectors. So it can be shown as A cross B cross C is equal to A dot C B A dot B C. Similarly, you can write A cross B cross C is equal to C dot A B minus C dot B A. Let's move on to vector integration. Vector integration. So first is line integral. Line integral is evaluated along the curve so let f be any differentiable vector a differentiable vector function defined along the curve C, then the line integral of f is defined by integral C f dot dr. Or if C is a closed curve, then it is denoted by a circle like this. Right? So in the Cartesian form, let f is equal to f1i plus f2j plus f3k and r vector is xi plus yj plus zk. Then line integral will be f1 dx plus f2 dy plus f3 dz. So this is called the Cartesian form of line integral. If f is a function of t, then f dot dr is given by f1 dx by dt plus f2 dy by dt plus f3 dz by dt right? Let us understand this with an example. So if we have to evaluate line integral where f is given as 2y plus 3i plus xzj plus yz minus x k where C is the curve x is equal to 2t square, y is equal to t and z is equal to t cube. Joining 0, 0, 0, 2, 2, 1, 1. Yes? So let us start differentiating x with respect to t, y with t and z with respect to t. So dx by dt is equal to 4 times t, dy by dt is equal to 1 and dz by dt is equal to 3t square. Okay. Now let's substitute the values of x, y, z in f. So we will have 2t plus 3 and 2t plus 3 where y is equal to t, x is equal to 2t square and z is equal to t cube. So t raised to the power 5. Yes, j plus yz minus x. Okay, t raised to the power 4 minus x, 2t square. Okay, so this is f. Now, since we know that line integral is f1 dx by dt plus f2 dy by dt plus f3 dz by dt. Okay. So, and where dx by dt we got as dx by dt, dy by dt, 4t, 1 and 3t square. Let us substitute the values. So, we will get 2t plus 3 times 4t. Okay. So, 8t square plus 12t plus 2t 5 raised to the power 5 plus and dz by dt is 3t square. So 3t square. So 3t raised to the power 6 minus 6 raised to t raised to the power 4 and dt. Yes. Now let us find the limits of t. So we know that y is equal to t. So if y is equal to 0, if y tends to 0, t also tends to 0, and if y tends to 1, t tends to 1. So you can choose any among these three. Y is equal to t, x is equal to 2t square or z is equal to t cube. You will get the same. right? So now we got the limit of t as 0 to 1. So t varies from 0 to 1. Okay, let us put this limit values here. T is equal to 0 to 1, right? So again, let us integrate this with respect to t. So we will have 8t cube by 3 plus 12t square by 2 plus 2t raised to the power 6 by 6 plus 3t raised to the power 7 by 7 minus 6t raised to the power 5 by 5 and 0 to 1. Yes? Okay. So again, by substituting the value of t, okay, this will be reduced to 288 by 35. So verify your answer. Next is path independence. So the line integral of a vector function f is said to be path independent if and only if p, q, r are continuous in domain D, are continuous in domain D, and if there exist some scalar function u in domain D such that f is equal to gradient u, or du del u by del x is equal to p, del u del y is equal to q, del u by del z is equal to r. So if this is the case, then the line integral of f along the curve C from A to B is given by the formula p dx plus q dy plus r dz is equal to u of b minus u of a. So that means line integral is path independent. Then for any closed contour, C, we will have f r closed integral dot dr is equal to 0, right? So vector field of the form f is called a conservative field, and the function u is called a scalar potential. Right? So next is surface integral. So any integral which is evaluated over surface is called surface integral. So let f be any differentiable vector defined over a surface. defined over a surface S, then the surface integral is defined by double integral f dot n ds, where n is the outer unit normal vector to the given surface. Okay, unit normal vector to given surface. Yes. So f dot nds is defined where r1 is the projection in xy plane, then dx dy by n dot k, and defined over r2 where r2 is the projection in yz plane, dy dz by n dot j, and also in r3 if r3 is the projection in zx plane. I. Yes. Let us understand this with an example. So we have evaluate f dot nds where f is equal to 4xzi minus y square j plus yzk, and S is the cube bounded by surface S is the cube bounded by right. So let us draw the cube in xyz plane. So if we have x, this is y and this as z. So let us draw okay, cube yes, and let us name the vertex A, B, C, P, Q, R, S, and this is origin O, right? So for PQAR, surface PQAR, okay, n is unit normal vector is I P, see this PQAR, okay. So this lies in the yz plane, so normal vector is I in the x direction, and since x does not vary, x is constant, okay. So f dot n is equal to 4xz, which is 4z, putting x is equal to 1, right? Okay. Now let us evaluate the integral f dot n ds is equal to y is equal to 0 and to 1, z varies from 0 to 1, 4x dy dz, because x is constant for PQAR. Yes. So now evaluating, we will have 4z square by 2, 0 to 1 and y 0 to 1. So which will be 4 times half into 1. So 2. Again for SBOC, this surface, for SBOC we have n is equal to, see for PQAR it was unit normal vector was directing towards x, positive x direction, and for SBOC unit normal vector will be directing towards minus x direction, so that is minus I, and since x is 0, x is constant and is 0, so f dot n is equal to minus 4xz, which is 0. So integral f dot n ds is also 0. Okay. Now for this surface PQBS, we have unit normal vector directing towards plus y direction, that is unit vector is j and y is 1, y is constant 1. So for PQBS we have n is equal to j and y is equal to 1. So f dot n ds is equal to x is equal to 0 to 1, x varies from 0 to 1, z varies from 0 to 1, and y square, let me go back, what is it, minus y square. Okay, so minus y square, which is minus 1 dx dz, right? So minus x 0 to 1, z 0 to 1, which is minus 1. So again for OCRA, unit normal vector will be j, OCRA will be minus j and y is equal to 0. So for OCRA, n is equal to minus j and y is equal to 0. So again integral is f dot n is equal to 0. Okay, right. So again for surface SPRC, okay, SPRC, so we will have unit normal vector as k plus k and z is 1, z is constant here. So for SPRC, n is equal to k and z is equal to 1. So f dot n ds is equal to, x is equal to 0, varies from 0 to 1, y varies from 0 to 1, and yz it is, I think. So yz is y only. Let me see. So what is it? Yz, yes. So since z is constant, so we have just y. So y dx dy. Okay. So integrate. So y squared by 2, 0 to 1 and x 0 to 1, so half. So again for BQOA, this surface, we will have unit vector as minus k, because the direction of unit normal vector is in minus z direction. So minus k and z is 0 and constant. So for BQOA, z is equal to 0 and n is equal to minus k. So f dot n ds is equal to 0 because it was yz, right? So now the final value of integration, surface integration is, add them up. So summing them up, all of them, so 2 plus 0 plus minus 1 plus 0 and plus half. So 2 plus 0 minus 1 plus 0 plus half. So which is 1 plus half is equal to 3 by 2. So this is the answer. Next is volume integral. So any integral evaluated over a volume is called volume integral. So volume integral is given by del dot f dv, where del dot f is the divergence of f. Okay, so let us understand this with an example. So f is given as 2x square minus 3z I minus 2xy j plus x k, where v is the region bounded by x is equal to 0, y is equal to 0, z is equal to 0 and 2x plus 2y plus z is equal to 4. Yes? So let us first find the divergence of f vector. So which is 4x, okay, and minus 2x, this will be 0. Now let us find the limits of the variable. So where z is equal to, you can write as z is equal to 4 minus 2x minus 2y. So in terms of x and y, z can be written as 4 minus 2x minus 2y. Yes? Let us show this planar surface on xyz plane. Since all the coordinates are positive, so this surface lies in the first octant. Let's say we have here 4, 2 and 2. So we need to set up bounds or limits on integration. So let us assume we are under the plane and in the first octant. So we have the limit for z. So 4 minus 2x minus 2y. Yes, or I simply wrote z in terms of y and x. Yes, this is x, y and z. So put z is equal to 0 for y, we will have 2 minus x. Okay. From here, if you put z is equal to 0, you will have y is equal to 2 minus x. Again, for x, we have 2 for after setting y and y is equal to 0 and z is equal to 0. Right? So now we have limits on integration. Okay, so we will rewrite del dot f was 4x minus 2x, that is 2x. So 2x dz dy dx. So z is varying from 0 to 4 minus 2x minus 2y. Y is varying from 0 to 2 minus x. X is varying from 0 to 2. So okay. So z depends upon x and y dependent upon only x, and x is independent. While evaluating, assume the other two variables as constant, and then you will have two xz, where z is 4 minus 2x minus 2y. So dy by dx 0 to 2 minus x, 0 to 2. So again, this is 8x minus 4x square minus 4xy dy. Now assume dx as x variable as constant. Yes. Okay. So y varies from 0 to 2 minus x, x varies from 0 to 2. So again, 8x, after evaluating you will have 8x plus 2x cube minus 8x square, and then dx, and 0 to 2. Now the triple integral is reduced to single integral, and this will come as 8 by 3. Yes. So check the answer. Next is Gauss divergence theorem. So the Gauss divergence theorem uses the connection between surface to volume integral. So if we have, let S be the closed surface enclosed by volume V, enclosed by volume V, and F be any differentiable vector function, then F dot n ds over surface is equal to volume divergence F dV, or del dot f dv. So Cartesian form of divergence theorem is f1 dy dz plus f2 dz dx plus f3 dx dy is equal to triple integral df1 by dx del f1 by del x plus del f2 by del y plus del f3 by del z into dx dy dz. Okay, let us have one example. So question: the value of surface integral axi plus byj plus czk dot nds. So where S is the surface of a sphere, x square plus y square plus z square is equal to 1. So find the divergence of f, so which is a plus b plus c. So f dot nds is equal to volume divergence f del dot f dv. So del dot f is a plus b plus c, and dv, you know the volume of sphere, which is 4 by 3 pi r cube. Okay, since r is 1 here, radius is 1, so 4 pi by 3 a plus b plus c is the answer. Okay, if f is a position vector r, so del dot r is equal to del x by del x plus del y by del y plus del z by del z. So which is 1 plus 1 plus 1 3. So integral, surface integral r dot nds is equal to volume integral del dot r dv, so which is 3v, 3 times volume. Okay, next is Stokes theorem. Stokes theorem. So Stokes theorem is the transformation between surface integral and line integrals. Transformation between surface integrals and line integrals. If f is a vector function, having component f1, f2 and f3, then and let S be an open surface bounded by a closed and non-intersecting curve C. Okay, so and f is any differentiable vector function, then closed integral f dot dr is equal to curl f dot nds is equal to double integral del cross F dot NDS. Okay. So where n is the unit normal vector of S. Okay. So this can be expanded as, rewritten as S. So we have F1, F2, F3 as the components. So del F3 by del Y minus del F2 by del Z, N1 minus plus del F1 by del Z minus del F3 by del X, N2 plus del F2 by del X minus del F1 by del Y, N3 du dv is equal to closed integral f1 dx plus f2 dy plus f3 dz. Let us understand this with an example. So evaluate by the Stokes theorem, where f is minus y cube I plus x cube j and S is a circular disc x square plus y square less than equal to 1 and z is equal to 0. Right? So let us find del cross f. So which is I, j, k, del by del x, del by del y, del by del z, minus y cube, x cube and 0. So we have already expanded this in the last slide, see. So let us expand I 0 minus 0 minus j 0 minus 0 again plus k 3x square minus k plus 3y square. So 3x square plus 3y square. So which is 3x square plus y square 2k. And we can directly say n is equal to normal vector, unit normal vector is k, because z is equal to 0 given, and that means xy plane, right? So, and also x square plus y square is less than equal to 1, since, so we can say this as 3k dot k ds is equal to 3s. So which is a circular disc, so area will be pi r square, where r is 1, so 3 pi r square, so 3 pi is the answer. Yes. So next is Green's theorem. So Green's theorem is the special case of Stokes theorem. The special case of Stokes theorem. So let f be a function, vector function f1 and f2 that is continuously differentiable in the domain in xy plane containing simple connected bounded closed region S and whose boundary is C, which is piecewise smooth simple closed curve. So then Stokes theorem now takes the form Stokes theorem takes the form double integral del f2 by del x minus del f1 by del y dA is equal to f1 dx plus f2 dy. Yes. So you can write dA as dx dy. Okay. Let us take one example. So find the value of 2x minus y dz dx plus x plus y dy. So where C is the circle x square plus y square is equal to 9. So this is a circle with radius 3 and del f2 by del x is equal to 1 and del f1 by del y is equal to minus 1. Del f2 by del x is equal to 1, del f1 by del y is equal to minus 1. So these are constant, so we need not worry about limits. So according to the Green's theorem, let us rewrite the formula is equal to del f2 by del x minus del f1 by del y yes. So this is equal to 1 minus of minus 1. So minus of minus 1 dA is dx dy. So which is 2 dA and we know that the C is given as circle with radius 3, so which has area as pi r square or pi into 3 square, so which is 18 pi. So 18 pi is the answer. We will see more problems in the next lecture. I will share notes on my Telegram channel. Please find the link in the description below. Okay, keep preparing. Thank you.